Welcome to the Deep Dive. Today we're diving deep into, well, a fundamental force of nature, one that shaped landscapes and history: earthquakes.
Absolutely. These events are just such a dramatic display of the power, the change happening right beneath our feet. A constant reminder the Earth is anything but static.
Yeah, definitely keeps you on your toes. Our source material for this deep dive is a pretty comprehensive article from Wikipedia.
Good stuff there.
Right. And our mission, as always, is to take this wealth of information and really unpack it for you. What are earthquakes? Why do they happen? How do we measure their, frankly, immense power?
And their effects, too, which can be so varied and sometimes quite surprising.
Exactly. And maybe most importantly, what can we do to live with them? We're pouring out the key nuggets of knowledge here.
And we'll dig into some fascinating bits like how different faults move, just how much energy these things release. We're talking like atomic bomb levels of energy, thousands of them. And some really unusual quakes, too, some that rupture faster than sound, and others that hide these deadly tsunamis. We'll even touch on how human actions can sometimes play a part.
Okay, lots to get through. Let's unpack this. So, to start right at the beginning, what exactly is an earthquake at its most basic level?
Okay, so fundamentally, it's the shaking of the Earth's surface. Simple as that
A
sounds.
shaking.
But why it shakes? That's the key. It happens because there's a sudden release of energy stored in the Earth's rigid outer shell. That's the lithosphere.
Right.
And this energy travels outwards from the source as seismic waves. That's the shaking you feel.
Got it. And the source mentions other names people use, like quakes, tremors, temblors. They all mean the same basic thing.
Pretty much, yeah. Different words for that shaking. And it also clarifies, which is interesting, that earthquake can technically describe any event that generates these seismic waves. So natural geological shifts, obviously, but also, say, large explosions or other human-caused events.
That's a good distinction. Natural versus human-caused.
Ah.
Okay, so for the natural ones, where does it start? There are specific terms, right? Hypocenter, epicenter.
Exactly. So the hypocenter, sometimes called the focus, that's the actual point deep underground where the rock first ruptures, the very beginning.
Okay, double.
Then the epicenter. That's the point on the Earth's surface directly above the hypocenter. That's the location you usually hear about in the news. You know, the epicenter was 10 miles west of.
Right, the map location. But the real start is the focus, deeper down.
Precisely. And scientists use a couple of terms to talk about earthquake activity in a region. There's seismic activity that's looking at, like, how often quakes happen, what types, how big they are over time.
Kind of the pattern.
Yeah. And then seismicity is a bit more technical. It's the average rate of energy released per unit volume of rock. Helps quantify how active a zone is.
Okay, helps characterize the risk, I guess.
Yeah.
So where does all this energy actually come from? How does it build up and then get released so suddenly? The science behind the shake.
Right. So the main driver for most earthquakes anyway is the rupture of geological faults. These are basically fractures in the Earth's crust where blocks of rock move relative to each other.
Because the tectonic plates are always moving, right?
Exactly. The plates are shifting, but the fault surfaces themselves aren't perfectly smooth. They have these irregularities, bumps, rough patches. The source calls them asperities.
Asperities.
Yeah.
Like sticky spots.
Yeah, that's a good way to think of it. These asperities cause the two sides of the fault to lock together, stopping them from sliding smoothly. But the plates are still trying to move.
So stress builds up.
Precisely. Stress builds up in the rocks around that locked section, storing energy, elastic strain energy. It's like stretching a rubber band further and further.
Uh-huh.
Eventually, that built-up stress becomes stronger than the asperities holding the fault locked. The fault suddenly breaks, slips, and bang, all that stored energy is released in the form of seismic waves.
Oh, okay.
Yeah.
The rubber band snaps. That makes sense. And this whole process, the buildup and sudden release, that has a name, doesn't it?
It does. It's called the elastic rebound theory. Gradual stress accumulation, then sudden rebound or release.
Elastic rebound. Got it. Now, here's something that really jumped out from the source. Only a small fraction of that total energy actually becomes the shaking we feel.
Yeah, it's quite remarkable. The source says something like 10%, maybe even less, of the total energy released actually goes into those seismic waves.
Only 10%. What happens to the rest?
Most of it gets used up breaking the rock itself, creating the fracture surface, or it's converted into heat because of the friction along the fault as it slips.
Wow. So the ground shaking, which can be so destructive, is just a fraction of the total event's power. Amazing. Okay, let's talk more about these fault lines then, where the action is. The source lays out three main types for interplay quakes.
That's right. The main categories are normal faults, reverse faults, which are often called thrust faults, and strike-slip faults.
Okay, let's break those down. Normal faults first. Where do they happen?
Normal faults occur where the Earth's crust is being pulled apart, extended. Think divergent boundaries, like mid-ocean ridges or continental rift zones.
Like in Iceland, maybe?
Exactly. That's a great example. Here, the block of rock above the fault plane slides down relative to the block below it.
And the quakes on these tend to be smaller. The source says less than magnitude 7 generally. Nice that.
It's often limited by how thick the brittle part of the crust is in those areas. Where the crust is stretching and often hotter, like in Iceland, that brittle layer that can actually break might only be, say, 6 kilometers deep. Less rock to rupture means less energy released, generally limiting the max magnitude.
Ah, okay.
Yeah.
Less depth for the break to happen. Makes sense. So what about the second type, reverse or thrust faults?
These are kind of the opposite. They happen where the crust is being squeezed together, compressed, so convergent plate boundaries where plates are colliding.
Right, like mountains being built.
Exactly. In this case, the block above the fault moves up and over the block below it. And when these faults dip at a shallow angle, they're called thrust faults. And these are associated with the most powerful earthquakes on the planet.
The biggest ones.
Yeah. The megathrust earthquakes, we're talking magnitude 8, magnitude 9, even larger. These are responsible for something like 90% of the total seismic energy released globally each year.
90%. Just from this one type of fault setting. That's incredible. So colliding plates, convergent boundaries, that's where the real giants happen.
Definitely.
Okay. And the third type, strike slip.
Strike-slip faults. Here, the two blocks of crust slide horizontally past each other. No significant up or down movement, mostly side to side.
Like the San Andreas fault in California.
That's the classic example everyone knows, yes. Transform plate boundaries are essentially huge strike-slip fault systems. These can also produce major earthquakes, potentially up to around magnitude 8.
Still very powerful, but maybe not quite reaching that megathrust scale typically.
Generally, yeah. The source notes that strike-slip faults often tend to be steeper structures, and the width of the fault zone that can rupture within the brittle crust is maybe more limited, perhaps around 10 kilometers deep. This can constrain the maximum possible rupture area compared to those really wide, shallow-dipping megathrusts, which can rupture over, 50 or 100 kilometers vertically down the dip.
Gotcha. So the geometry limits the potential size compared to megathrusts. And the source also mentions oblique slip.
Right, that's just a combination. Most halts in reality aren't purely normal, reverse, or strike slip. Oblique slip means there's a mix of vertical dip slip movement and horizontal strike slip movement happening on the same fault during the quake.
Makes sense. Reality is usually messier.
Exactly. And one more key point here. It's really only the cooler, brittle parts of the Earth's crust and those subducting slabs diving into the mantle that can store up this elastic energy and then release it suddenly in a rupture.
Right, because hotter rock flows instead of breaks.
Precisely. Once you get down deep enough, typically where temperatures are above about 300 degrees Celsius, the rocks behave more like, extremely thick putty. They deform ductily, they flow, they don't snap catastrophically.
Like trying to break hot taffy versus cold glass?
Yeah.
Good analogy. The source also added a little detail about the stress levels needed for each fault type.
Ah, yeah, that's interesting. Thrust faults, because you're pushing rocks up against gravity and compressing them hard, they generally require the highest levels of stress to make them rupture.
Okay.
Strike-slip faults need sort of intermediate stress levels, and normal faults, where the crust is being pulled apart, actually require the lowest stress levels to initiate slip, because gravity is kind of helping pull the upper block down.
Huh. That relates to the forces involved and maybe how much energy gets released too.
It can influence the stress drop during the quake, which is one factor controlling the energy release, yes.
Right. Speaking of energy, let's really try to grasp the sheer power involved. We use magnitude scales, like the moment magnitude scale today, but it's not intuitive how much energy increases with each step.
No, it's definitely not linear. This is where it gets mind-boggling. Each whole number increase in magnitude represents roughly a 32-fold increase in the energy released.
32 times, not just double or something.
Nope, 32 times. So a magnitude 6 quake releases about 32 times more energy than a magnitude 5. A magnitude 7 releases about 32 times that, meaning it's roughly 1,000 times more energetic than a magnitude 5.
Wow, that exponential jump is just hard to wrap your head around.
It really is, and the source gives that incredible analogy to try and convey it.
The atomic bomb one? Yeah, read that. An M8.6 earthquake releases energy equivalent to, what was it, 10,000 World War II-era atomic bombs?
10,000. That single comparison gives you such a visceral sense of the colossal forces we're talking about deep inside the Earth.
10,000 bombs
Mm.
in one earthquake. Just staggering. So magnitude is linked to the rupture area. How big the patch of fault is that slips and how much it slips, the stress drop. And you mentioned the width of the rupture is often key for the maximum possible magnitude.
Yeah, particularly the down dip width, how far the rupture extends vertically. Those really wide rupture zones, maybe 50 to 100 kilometers or even more, that are possible on the shallow dipping megathrust faults at convergent margins. That's what allows for the truly enormous M9 plus earthquakes, like the ones off Japan in 2011 or Alaska in 1964. A larger area means much more energy released.
Location, location, location.
Yeah.
Not just on the map, but also depth matters, right?
Yeah.
Focus depth. How does the source classify quakes based on how deep they start?
Right, there are three main categories. Shallow focus earthquakes. These start less than 70 kilometers deep.
Okay. Relatively near the surface.
Yeah, and this is where most tectonic earthquakes happen, especially around the active plate boundaries like the Pacific Ring of Fire, that brittle upper crust.
Makes sense. What's next?
Then you have mid-focus or intermediate depth earthquakes. These occur between 70 and 300 kilometers down.
Hitting deeper.
And finally, deep focus earthquakes. These are the really deep ones, starting between 300 and 700 kilometers below the surface.
700 kilometers. Wow. But wait, didn't we just say rock below about 300 degrees Celsius starts to flow instead of break?
Yeah.
How can you get a brittle snap, an earthquake, way down there?
Yes. That's a great question, and it's been a puzzle in seismology for a long time. These deep focus quakes don't just happen anywhere. They occur specifically within those cold, dense oceanic plates that are sinking or subducting back into the mantle.
The Wadati-Benioff zones.
Exactly. So even though the surrounding mantle rock is hot and ductile, the subducting slab itself stays relatively cool and rigid for quite a while as it plunges deeper.
So the slab itself is still brittle enough, even way down there.
Well, it's thought that it remains brittle enough, or perhaps other mechanisms come into play under those extreme pressures and temperatures. One leading hypothesis mentioned in the source involves something called a phase transition.
Phase transition. Like water turning to ice.
Sort of, but with minerals. The idea is that olivine, a common mineral in the mantle, might suddenly transform into a denser crystal structure under the immense pressure deep within the slab. If this change happens rapidly, it could potentially trigger a sudden slip or faulting, causing a deep earthquake.
A mineral changing its structure triggers a quake. That's fascinating. A possible answer to the deep quake mystery. The source also mentions quakes linked to volcanoes.
Yes, definitely. The movement of magma, fluids, and gases beneath a volcano can cause the ground to shake. These are usually shallow tremors and quakes, often occurring in swarms. Sometimes tracking these volcanic earthquakes can help scientists monitor volcanic unrest and potential eruptions.
Right, a warning sign. Okay, let's switch gears slightly and talk about the rupture itself. Once it starts at the focus, how does it spread?
Yeah, so the rupture begins at the focus and then propagates or spreads across the fault surface. You can kind of picture it like a crack spreading through glass, but on a geological scale. It continues spreading until it hits something that stops it. That could be the edge of the stressed area, or a part of the fault that's stronger or perhaps creeping smoothly. Or maybe it reaches the boundary between brittle rock and ductile rock deeper down. For really big quakes, the rupture might even break all the way to the surface.
And the speed of this rupture spread is important too, isn't it? The source mentioned some really unusual speeds.
It is. Normally, the rupture front travels along the fault at a speed that's slower than the shear waves, the S waves, that are generated. But scientists have observed what are called super shear earthquakes.
Super shear. Faster than the S waves.
Exactly. The rupture actually outpaces the shear wave velocity in the surrounding rock. It's like it's breaking the sound barrier for shear waves in a way.
Wow. That sounds incredibly energetic. Does that have specific effects?
It's thought to. The source mentions a potential for a kind of geological sonic boom effect, which could lead to more intense shaking in certain directions. These have been observed in some large strike-slip events, and the source notes that aspects of the devastating 2023 Turkey-Syria earthquakes might have involved super shear rupture.
A geological sonic boom. Incredible. What about the other end of the spectrum? Slow ruptures.
Yes, slow earthquakes. These are ruptures that happen much, much more slowly than typical earthquakes. Instead of lasting seconds, they might unfold over hours, days, or even weeks.
Slow. Does that mean less dangerous?
Not necessarily. There's a particularly dangerous type called a tsunami earthquake.
Tsunami earthquake. Why is that one dangerous if it's slow? That seems counterintuitive.
It's dangerous because it's slow, in a way. The slow rupture can still displace a huge area of the seafloor, generating a massive tsunami. But because the rupture itself is slow, the ground shaking felt on nearby coasts might be relatively weak.
Ah, so people don't get the natural warning sign of strong shaking.
Exactly. They might feel little or nothing, not realize the danger, and then hours later, a devastating tsunami arrives. The source mentions the 1896 Sanriku earthquake off Japan as a tragic example of this weak shaking, but a catastrophic tsunami that killed tens of thousands.
That's a chilling combination.
Oh.
Wow. The source also brings up something about fluid pressure during a quake, co-seismic overpressuring.
Right. This is really interesting. During the incredibly fast slip on the fault, the friction generates immense heat. If there's groundwater trapped in the fault zone, this heat can actually vaporize it almost instantly.
Turning water to steam inside the fault.
Pretty much. This drastically increases the fluid pressure within the rock's pores and fractures. That's the pore pressure. And high pore pressure can effectively lubricate the fault, reducing its strength and influencing how it slips.
The water trapped in the rock actually affects the earthquake rupture itself.
It seems so. And it doesn't necessarily stop there. The source explains that after the main shock, this zone of high fluid pressure can slowly spread outwards through the surrounding rock's fracture network.
And that triggers aftershocks.
It's thought to be a major mechanism for triggering aftershocks, yes. As the high-pressure pulse moves, it can change the stress on nearby patches of the fault system, pushing them towards failure.
And this links back to human-caused quakes too, right? Injecting fluids.
Exactly. This whole concept of changing pore pressure is key to understanding induced seismicity. When humans inject fluids deep underground for things like wastewater disposal from oil and gas operations, or during hydraulic fracturing, or even filling large reservoirs behind dams, they are increasing the pore pressure in the rocks.
And that can unclamp existing faults.
Precisely. It reduces the friction holding faults locked, potentially allowing them to slip and cause earthquakes, even in areas that might not have had significant natural seismicity before. The source explicitly mentions the M5.7 earthquake in Oklahoma in 2011 being linked to wastewater injection.
Yeah, Oklahoma had a huge spike in quakes.
It did, largely attributed to this practice. The source also brings up the potential link, though it says it's not definitively proven, between the massive M8.0 Sichuan earthquake in China in 2008 and the filling of the nearby Zipingpu Dam reservoir a few years earlier, changing the stress and fluid pressure regime.
So our activities, even seemingly unrelated ones like building a dam or disposing of waste, can actually interact with the Earth's stress field and trigger quakes. That's a really important connection.
It absolutely is.
Okay, let's talk about how earthquakes often don't happen in isolation. They come in sequences or clusters.
Very true. Quakes in a particular area are often related in time and space.
The most familiar sequence is probably main shock and aftershocks. What defines an aftershock?
Aftershocks are simply smaller earthquakes that occur in the same general region following a larger earthquake, which we call the main shock.
Why do they happen? Is the main quake finished?
The main shock drastically changes the stress distribution in the surrounding crust. The crust is basically adjusting to this big shift. Aftershocks are the result of smaller readjustments and failures on nearby faults or patches of the main fault that didn't slip initially.
And they're always smaller than the main shock.
By definition, yes. But they can still be large enough to cause significant additional damage, especially to buildings already weakened by the main event, and they can continue for days, weeks, even years after a very large main shock.
And the source clarifies an interesting point. If an earthquake happens that you thought was an aftershock, but it turns out to be bigger than the original one,
then you have to reclassify. The bigger one becomes the new main shock, and the original one is then called a foreshock. It's all relative to the largest event in the sequence.
foreshock, main shock,
Yeah.
aftershock. Got it. What about earthquake swarms? The source mentions Yellowstone as an example.
Swarms are different. They're sequences of many earthquakes occurring in a specific area over a relatively short time, days, weeks, maybe months. But crucially, there's no single main shock that clearly stands out as much larger than the others.
Just a whole bunch of similar-sized quakes clustered together.
Exactly. It's more like a burst of activity without a dominant event. The source gives examples like volcanic areas, such as Yellowstone, where magma movement might be involved, or